associated with the rifting of the North Atlantic. That started the warming, and then that set off a series of positive feedbacks that intensified the warming. And it could have been all of the above, plus permafrost melting on Antarctica, which is another one that's been suggesting. And those amplified the warming. Okay. So we got into this and were interested in finding a place where we could develop a record of the PTM that wasn't so disrupted by the factors that were affecting the deep sea carbonate record, and so and primarily in terms of dissolution. So we had questions that we wanted to answer that required a more continuous record. We're interested in, as everyone else is, what was the total amount of carbon added, and at what rate was carbon added to the system? Because if we want to make this as an analog for modern fossil fuel burning, we have to understand how fast carbon was being added and how much carbon was added to the system. We understand that we're working with a time period 56 million years ago, and so we need to quantify all of this. We need to understand, for example, how sensitive these estimates are, and also how sensitive the Earth's climate system would have been to a carbon addition at a time period that, for example, had no continental ice sheet. So it's a much warmer interval to start with. And so what would be the climate sensitivity at a time period when you don't have ice sheets? What would be the response of the ocean to a carbon addition for a time period that might have had a very different distribution of calcium carbonate on the sea before the event? Oh, I'm on a timer all of a sudden. Something clicked that. So we went to the Arctic, and the work I'm going to talk about now is a former graduate student of mine, Ying Sui. We worked on some cores that we stumbled upon in Longyearbyen from the local coal company. These are shales that were deposited in a marine basin here, the central tertiary basin of Spitsbergen. So these are clastic sediments, clay-rich deposits, but they are organic rich, 1 to 2 weight percent organic carbon, and so we analyze the organic carbon isotopes from these sediments. Whoa, something's keep me moving. Is that you, Gene? Keep me on pace. That's good. I'm dragging. So here's the record that we were able to put together. And one of the things I should have pointed out from that Walvis Ridge section is that the PTM is about this thick. Okay, maybe 1 to 2 meters thick, and the actual onset of the event is just a few centimeters, and it's been dissolved. In Spitsbergen here, this is a clastic sedimentary sequence, and the width of the PTM here is, well, that's 542 meters there, and that's 488. So it's about 60 meters thick, and so the tape recorder is running at high fidelity. And this is an organic carbon record with fairly continuous organic carbon deposition. So we have a much higher resolution, holy mackerel, record of this carbon isotope event. And so we've analyzed this, and now we've been using this isotope record to model the rates of carbon addition and the consequences for the marine environment of that carbon addition to try to match it to the observed rates of dissolution around the world and try to come up with an answer to those questions. Okay, so one of the first things we had to do is convert this record, which is in depth space, into time, and so we used X-ray fluorescence measurements of the iron, manganese, and calcium contents of those cores to do time series analysis to pull out the Milankovitch orbital frequencies from these records, which allowed us to put this in a temporal framework. So if you've heard about Milankovitch, Earth's orbit varies on various timescales, 20, 40, and 100,000 years, in its orbit around the sun, the tilt, the eccentricity, and the precession of the spin axis all have predictable periods, and you can use those as an orbital chronometer for the sedimentary record. And so we've done that in collaboration with colleagues at Southampton University, and so we were able to convert this depth record into time. And so now, for example, we have a fairly continuous record of the onset of the event, lasting about 20,000 years, which is very important because it's this onset of the event, this drop in the delta 13C of the ocean atmosphere system that is the time period in which the fossil carbon is being added to the system. So we have that well resolved, and then also the pace of the recovery from that event. And then what Ying did, which was probably the most novel part of her dissertation, was to take an Earth system model of intermediate complexity. So this is a general circulation model at coarse resolution of the ocean with a full biogeochemistry implemented in it, driven by an energy and moisture balance, very simple climate model. And so we have a climate model that can address the effects of rising CO2 on the climate system, and then we have an ocean model that can look at things like the change in pH and saturation state of the ocean. We can also look at changes in ocean circulation rates associated with the warming, with hydrological changes associated with the warming, and also look for the spread of anoxia. And I won't talk about most of that today. But this model, again, was developed in the UK, mostly by colleagues at Southampton. And then the biogeochemical part of this was developed mostly by Andy Ridgewell, who was at Bristol and is now at UC Riverside. And we've been working with him for many years to refine the biogeochemical components of this model. What Ying did that was really the first of its kind was to, rather than run this as a forward model where we would impose some sort of forcing on the model and run it forward, she worked with Andy to develop a way to invert the model so that the model was forced to track the carbon isotopic record that we had developed for what we thought the atmospheric CO2 delta 13C was through this event. And so every time step in the model adds a certain amount of fossil carbon of a prescribed isotopic composition, whether we're trying to simulate the methane addition or the organic carbon source, and so it can track that record. And so this is really the first time I think that a GCM has been forced to run as an inverse model, and it worked very well. And so we were able to address some of these questions of whether or not what might have been organic matter or methane. And there were some things that matter here that I think I'm not going to go into, but it turns, so she ran a whole suite of simulations. I'm going to show you the two that fit the record the best. One was with methane, where we have a very light isotopic composition, and this was the total amount of carbon that needed to be added in that event. And then the other was peat and coal at minus 22, about 7,000 gigatons. And it's interesting that those two forcings require two different initial conditions of the model, which is really more in the detail for the aficionados. But with only a smaller amount of carbon added to fit the geologic record of this event, we needed to start out with a much shallower CCD before the event. In other words, much less buffering in the ocean prior to the event to track all of the geological records or to fit the data the best. Whereas with a larger carbon addition, one might imagine that the ocean, to track the record, must have been more well buffered. And so this gets at that, what was the nature of the early Cenozoic ocean in terms of its buffering capacity for ocean acidification. Anyway, these are just some of the results. Here's the isotope record, just demonstrating that we tracked that isotope record very well within the model. The black curves here, this is the rate of carbon addition if it had an isotopic composition of minus 22, and this is the record if it was methane. And as you might guess, if the source of carbon, most of the carbon is mostly methane, the rates of carbon addition are very small compared to those that are required to track the event if it were a heavier isotopic source like peat or coal. To kind of get to one of the main conclusions of this study, if you look at these rates, so the peak rate of carbon addition we simulate for this event with this heavier source is 1.5 petagrams per year, 1.5 gigatons per year. Modern fossil fuel burning is about 10. Okay, so we'll return to that in a little bit. The total amount of carbon added in that event over 20,000 years was about 12,000 gigatons. Modern fossil fuel reserves are more like 3,000 to 4,000. Okay, so the rate of addition was slower, but because of a 20,000 year event, the total amount of carbon added was more if it was peat or coal. If it was methane, of course, everything was less. The CO2 change, atmospheric CO2 change that we predict from this model with the coal or peat forcing is about up to 4,000 parts per million CO2, whereas if it was methane, it was a much more modest increase in atmospheric CO2 levels. Okay, this is the surface temperature response, and to get the sort of 5 to 6 degree warming that we want, we get a much better fit with the peat or coal. The methane release there's so little carbon because methane has such a strong lever on the isotopic composition of the ocean atmosphere system. It doesn't take a whole lot of methane at minus 60 to drive the ocean down by 4 per mil. And so we don't add much carbon as methane. Methane's very short-lived, and so the long-term climate effect of methane is after it's been converted to CO2, and that only gives about a 2 degree warming. And so from the point of view of the observed warming, this larger input associated with a isotopic composition more like peat or coal seems to fit the data better. Okay. Saturation states here are shown here. We model both the carbonate content of sediments and and you can see here that in our preferred scenario here, we can generate the sort of dissolution that you see. This is weight percent carbonate from 60 to 0. So I'll just focus on this simulation here. And there's a lot of extra detail here. You see that the carbonate content globally average drops to near 0 during the event and then recovers quite quickly. And one of the other interesting features of the modeling that actually is very satisfying is that what you find out with the model is that you actually overshoot the initial condition. And the ocean's CCD drops below where it was before the event for several tens of thousands of years, and then finally restores to the initial condition. And this is actually what we would expect the ocean to do in response to a big slug of CO2 being added, because that carbon dioxide that's been added to the ocean atmosphere system has to be ultimately removed from the system, and the way that it gets removed is to oversaturate the ocean to get that additional calcium carbonate drawdown that ultimately removes carbon from the system. And so this sort of extra behavior is what we'd expect, and interestingly, throughout the ocean, what's been noted in deep sea drilling project cores is a very white band just at the end of the PTM where the carbonate contents in many deep sea cores go to nearly 100%, rising from the pre-excursion value of maybe 80 to 90%. So there's a carbonate dump that's been observed through ocean drilling that we can reproduce with these models, and it's just the way the ocean atmosphere, in this case involves weathering of the continents, responds to a warming event driven by CO2 that then required the ocean become supersaturated, in a sense, to remove all that carbon from the system before it gets restored to its initial condition. Here, just to show you some of the dynamics of the model, this is the saturation state of the ocean at a depth here of 1,600 meters. These are the model results now, of course. And so here's the initial saturation state. We don't do too well with the Tethyan Ocean. It's on this coarse resolution model, doesn't get resolved very well. But you can see general supersaturation of the ocean at 1,600 meters depth before the event, and then here is the saturation state at 1,600 meters of the ocean. So widespread undersaturated conditions, with blue being, the blue-yellow transition being the transition from oversaturated to undersaturated. So much of the intermediate depths of the ocean became undersaturated at that point. And the saturation horizon rose to within a few hundred meters of the surface. So a very different world, briefly, during this event than what you normally think about in terms of the carbonate system of the ocean. Here's that interval then in the overshoot where the ocean becomes highly supersaturated as weathering brings in all this alkalinity that needs to be deposited as calcium carbonate, and then the model restores to the original state. And if we look at this in cross-section through the Atlantic close to Walvis Ridge, you can see here what happens. So here's before the event, same color scheme here. Blue is undersaturated waters. We have some intermediate water undersaturation in the oxygen minimum zone of the ocean and deep water undersaturation. South is to the left, North Pole to the right. And then as we go through time here, we'll see as we're injecting CO2, we see the saturation horizon rise dramatically to very shallow depths, essentially to the base of the wind mix layer of the ocean. Here at the peak of the event, it then quickly recovers, and you can see here now the saturation horizon goes to the bottom of our modeled deep sea floor during this overshoot event and then comes back up to the initial condition. So that's what we've been simulating. We've had this problem that's been really a bothersome part of this whole story, that we have more unknowns than we have constraints on the system. I've shown you scenarios where it was methane or where it was a peat or coal source, and we can't resolve which of those. Given the data constraints we haven't been able to constrain which of those two scenarios fits the data the best. You saw that, in our opinion, the peat or coal source of carbon, the much larger addition that led to much greater acidification, fits the temperature history much better than does methane, but that's still a point that's been argued. What I show this very busy graph here, it's from Don Penman's interesting work. He's been looking at boron isotopes. I don't know if you hear much about boron isotopes here, but the boron isotopic composition of calcium carbonate is sensitive to the pH from which that water was, which the carbonate was precipitated. And to make a long story short here, the boron isotopic composition of, and this is now time going forward to the left from this core, drops dramatically and then has that characteristic long recovery during the PTM. And so what Penman has been able to do with the boron isotopes is to provide yet another constraint on the carbonate system that we haven't had, the pH surface waters. And with this constraint, which is a pH drop of about a half a pH unit, so a significant drop in the pH of surface waters, we have that one extra constraint that, together with the carbon isotopes, should be able to finally help us decide whether or not, what was the source of carbon, how much carbon was added, and what were the effects there. Now, the other point of this, though, is that these are all really slow additions. This is over 20,000 years, and one of the things that's a little bit hard to pull out from this diagram, but because it's so busy, but this is the pH change, rapid drop and a slow recovery. This is the saturation state. And so one of the interesting things about this is that the saturation state of the ocean responds much more rapidly and recovers much more rapidly than does the pH. And this brings up an important point, is that the pH of the surface ocean is largely driven through equilibration with the atmospheric PCO2. And the atmospheric PCO2 stays high for a long period of time. The alkalinity of the ocean and the saturation state recovers on the time scale of alkalinity adjustment of the ocean, which is a factor of 10 faster than the total carbon adjustment. And so we see here that the ocean's saturation state recovers very quickly, becomes actually very high in this particular case as a result of the involvement of weathering of the continents and the dissolution of the seafloor and the buffering of the system. So this is maybe a diagram that's way too complicated to look at, but it's again making this case that the response of pH is not necessarily tracking the response of the saturation state of the ocean, and the saturation state of the ocean doesn't track the CO2 and temperature all that well either. In other words, the saturation state is much better buffered than is the pH or CO2 content of the atmosphere. And these are just a bunch of model simulations that, on second thought, I shouldn't have shown you. If you want to read a good paper, there is a paper by Berbel Honish et al. I'm a co-author of this 2012 science paper that lays all this out for you in greater detail. So if you want to follow up on that, why don't you go ahead and have a look at that paper. I won't burden you with that slide here. So anyway, wrapping up then, how do we pull this all together? And this is from a Scientific American article I wrote a few years ago. So this is meant to reflect the temperature change, but it's also reflective of the rate of carbon release over time. And this is our reconstruction of the initial phases of the PTM, warming over about 20,000 years with a total temperature rise of 5 to 8 degrees Celsius. This is the projected change in global average temperature forced by fossil fuel burning at rates about 10 times higher than today. In fact, rates that accelerate beyond 10 times higher than the PTM. And so the point being here that although the total magnitude of projected warming is comparable to the PTM, the rate of change is dramatically faster, at least on this initial phase of the curve. And I should point out, here we are today, barely above the noise of what we would predict from the geological record of the PTM. We have a carbon isotope shift, which I neglected to show you, which tracks just exactly what you would expect from the PTM of this much of the event having played out so far. In other words, the carbon isotopic composition of the atmosphere and surface ocean is falling at the pace of the PTM change for that same change in CO2 level or temperature. And so the PTM from that point of view serves as a good analog for the future. The problem is that the rate of change, at least according to our assessment to date, is maybe 10 times slower than fossil fuel burning. And so when we look at the geological record, and this is often brought up in terms of skepticism about CO2's effect on global warming and ocean acidification, we have a time period like the Cretaceous, which was a time when the geological proxies say that it was considerably warmer than today, and the CO2 content of the atmosphere was much higher than today. And the question is, well, but it's also the Cretaceous means chalk. It was a time of widespread calcium carbonate deposition. How can, if ocean acidification is going to impact calcification, how can the Cretaceous be explained? And the difference there is that the Cretaceous was a prolonged interval of very high CO2 driven by volcanic activity, prolonged volcanic activity, and on those timescales, as I've demonstrated to you for the PTM, the carbonate system can adjust. Weathering on land can bring in the alkalinity that's necessary to sustain saturation states at modern levels like today, despite there being a CO2 level that's maybe 10 times higher than today and a pH that's considerably lower. So as you probably learned through your marine chemistry classes, the carbonate system is not just dependent on pH. You can create a high pH undersaturated solution, a high pH supersaturated